Lesson 4, the in-betweeners. In our jump start, we're reminded how to find the missing term of a geometric sequence. So what we want to do is we want to start our equation with the first number we have on the y, and then count how many times we would have to multiply by r. 1, 2, 3. Take r to that power. And then on the other side of the equal side, this is where we would finish up at 320. Now, when we divide by 5, we're basically turning this into a single jump. We're saying that if you had 5 and you multiplied it by 64, you would get to 320. So how do we take 64 and break it up into 3 factors? Each of the factors equal to each other. Well, we can't just divide by 3 because this is multiplying. But what we can do is turn to our calculator and do the cube root of 64. Here's what that might look like. And I press the cube root button and type in 64. So the number is 4. R is 4. Now I can fill in the missing boxes. 5 times 4 is 20, 20 times 4 is 80, and 80 times 4 is 320. Explicitly, that would be the function f of n. It starts at 5, you multiply by 4, and you take it to the n minus 1 power. Since we're starting at 1. Quick little review of exponents here. 2 to the 3rd times 2 to the 5th is 2 to the 8th. Because if we did it the long way, 1, 2, 3 twos, and followed by 1, 2, 3, 4, 5 twos, is a total of 8 twos. So in general, when you have the same base, you add the exponents. Now, in our lesson today, what we're going to do is we're going to take this function. Here it's given to us recursively. F of 0 is 4. And here is our recursive expression. So start with 4 and double. So to 8, to 16, to 32, to 64. That would be 4 times 2 to the n minus 1. Now, we're going to graph those points. 0, 4, 1, 8, 2, 16, 332, and 464. At the end of the lesson, you're going to see a big graph. And we're going to have to just approximate where that would be. So 0, 4, and then 1, 8, 2, 16, 3, 32, and 464, way up here. So it looks like that. Well, the lesson's name is the in-betweeners. So we're going to talk about what happens in between those points. We're going to take the point of view of 2 students. One student's name is Travis, the other one is Tehani. Travis has this idea. He says, okay, look, we have this already in here. Well, what if we just find the halfway points? Oops. So in Travis's point of view, he says, what if we just find the halfway points? So halfway in between 4 and 8 would be the number 6. And, an easy way to find the halfway point is to take the average, which means to add the 2 endpoints together and divide by 2. So that'll work pretty good. I think this one is 12. And then halfway between 16 and 32 is 24. And halfway between 32 and 64 is 48. How well does this work? Well, the only way to really tell is to go back to the graph and plot those numbers, those in-between numbers. So 1/2 is 6. So basically 6, 12, 24, 48. If you notice, the blue ones are doubling. You can see from this Desmos graph that, okay, this point missed. This is one of Travis's points. It missed. And there's another one. In fact, they all miss. They're all not accurate. They're close, but what's happening is that Travis is trying to make a straight line where there is a curve. And so his method ultimately is going to fail. So in commenting on Travis's idea, it doesn't work. It is inaccurate, but it is close. Now, Tehani suggests that they should fill in the data in the table in a different way. She says, I notice the function increases by the same factor each time x goes up 1, and I think this property should hold over each half interval as well. So if what we do here is, if we fill in the table what we know, and then we're going to make a little equation to find the missing part, or the in-between part. And that would be 4, and we go 1, 2, so r squared equals 8, divide by 4. We get r squared equals 2, and then we can take the square root of both sides of the equation, and we don't have to write a little 2, but there's a little 2 here. That is the ratio. That is the missing number. So the square root of 2 is a number that goes on. It's a decimal that goes on forever. It never repeats. It doesn't have a pattern. So the most accurate thing we can say is that this is 4 times the square root of 2. And that comes from just multiplying 4 times that ratio. If you take 4 times the square root of 2 and you multiply it by another square root of 2, you will get to 8. And of course, you can put a decimal in there. All you do is take your calculator and type in 4 times the square root of 2. You probably want to round that off, and you'll get approximately 5.66. So each number times the square root to get the next one. 16 square root of 2, 32 square root of 2. And yes, we could approximate with decimals, and what we'll find is that, yes, that does hit the graph exactly where it's supposed to. If she wanted to break it up into thirds, no problem. Do the same thing. So this would be 4, 8, 16, 32. And we say 4 times 1, 2, 3, r to the third equals 8. All that does is that makes, if we divide by 4, that makes r to the third equal to 2. And you take the cube root of both sides. R is the cube root of 2. It's about 1.26 or so. So we just keep filling these in, take the previous number, and multiply it by a cube root of 2. And even here, we can say a cube root of 2 twice, take it to the second power, and so on and so on. We can fill in the decimals if we wanted to. So the constant factor to complete the table in problem number 6 was the square root of 2, and the number in this problem right here, 7, is the cube root of 2. Tehani and Travis make this connection to the function. And this really is the key learning from this lesson, is that when you have a 1/2 power on a number, that's the same as taking the square root. And if you had a 1/3 power, that would be the same as taking the cube root, and so on. So we're going to skip down here to the bottom under our takeaways. Today, I found a meaning for rational exponents that are non-integer fractions. Actually, before that, in the past, we used positive integers as exponents. So for example, 2 to the third, it meant to multiply 2 times itself 3 times. But now, we can take 2 to a 1/2 power. And that means the square root of 2. Let's prove it. The square root of 2 times the square root of 2 is 2. We know that because the square root is the number that when multiplied times itself gives you 2. But according to the laws of exponents, 2 to the 1/2 times 2 to the 1/2, we would be adding together the exponents. 1/2 plus 1/2, that would give us 1. So then these two must be equal to each other. They have to be. So our rule or our law of exponents now becomes something like this. If we have a root of a number, a, that's the same thing as taking a to the fractional power. And also, if we have that root taken to a power, then that power just transfers right along. But the root becomes the denominator. That's the key learning today. See you next time.